Thank you to the organizers for inviting me to this great workshop. It's already been a lot of fun. I'm going to talk about the Lasso, some algorithms and applications. And this is joint work with lots of people. Trevor Hasty and Jerome Friedman, my long-term collaborators, and also a bunch of grad students whose pictures are here. I have a great lab right now, grad students from all around. Two from the US and one from Australia, one from Germany. And they're all working on the Lasso and variations of it. So it's a great fun time right now. So if you're looking to hire some students, there are some great ones. And here's, I guess these pictures are a bit old, but here's my main collaborators, Trevor Hasty. Actually, the one on the Friedman's on the left. Actually, I did do a search on this website called myheritage.com, and I did come up with Fabio. So that's the match. You can see the similarity, kind of. There's a few years and hair follicles in between, and there's today's pictures of Trevor and Jerry. Okay, so what am I going to talk about? Well, the Lasso, I'm going to review it and talk about a new algorithm that we've come up with in the last year that really is, I think, exciting because it allows application of the Lasso in large problems for the first time. So it's very simple, and as we'll see, like it's so simple that a lot of us didn't see it for a long time, right? But it's extremely fast and useful. And I think because of its speed, it'll allow application of Lasso-type algorithms, procedures to large problems. And then I'm going to give three examples of application. Well, the first is an application of this pathwise coordinate descent to logit model for 0-1 data, especially useful for in genomics. And then I'm going to talk about the graphical Lasso, which is amazing how the web is. That we just published this about 6 months ago, but already people seem to know about it, and I've heard a couple mentions of it in the workshop already. And then the fused Lasso, which is another variation on the Lasso, useful for signals and 2D data. So I'll talk about these in turn, but I'm going to start off with this, with the pathwise coordinate descent algorithm for the Lasso. Well, let me first review the Lasso in regression. So we've got a response variable y and features xij, and the idea of the Lasso, of course, is to do least squares with a sum of the absolute values constraints on the coefficients. So you can write it as a constraint or a Lagrange multiplier equivalently. And you've got a tuning parameter lambda to choose. And the point of the Lasso is that by using an absolute value constraint, it constrains the coefficients in such a way that some of them can be zero. They'll be forced to be zero. And this is useful it's useful to select variables. It's also useful for the case, which is often in this workshop where p is bigger than n, where the least squares doesn't have a unique solution. And by putting on this constraint, you choose the solution with smallest L1 norm. Right? And it's a little bit subtle why this absolute value constraint works compared to, say, a Euclidean norm. And this next picture, which was in my original Lasso paper, is helpful there. So here's ridge, which uses a square constraint. Here's the overall least squares estimate. Here's the squared, the contours of the squared error loss function. Here's the place where the sum of the squares of the betas is less than or equal to a constant, the region, right? So ridge says, find me the first place the contours hit this region. And this region is smooth, it has no corners, so you're not likely to hit exactly at a place where one or the other is zero. The Lasso, on the other hand, uses the sum of the absolute values of the betas, which gives you this constraint region. It has corners, so it says, find me the first place these contours hit this green region. Now there's a reasonable chance you'll hit at a corner. Of course, here is where beta 1 is 0 or beta 2 is 0. High dimensions, that becomes, what's the word? Some kind of polyhedron, which has flat faces and corners, and if you hit at a face or a corner, if you hit at an edge or a corner, you've got something equals 0. Right? So it's basically the fact that this is not smooth and this is, that means the absolute value constraint is helpful in getting you a sparse solution. Okay? So that's by way of review of the Lasso. This is just a little example to get us started, which is this is in our data mining book. This example, we've got n equals something like 60 observations, nine measurements of PSA in men, log PSA in men. And this shows the Lasso solution as the bound evolves from 0 up to the least squares estimate. So each of these is the profile of a coefficient. Here are the least squares estimates. When there's no constraint, here's where there's 0, because the constraint is 0. And then in between, as you make the constraint looser and looser, the coefficients become non-zero. And they do so in a way that they're in this fashion. So this guy's immediately non-zero. Everyone else is 0 until this point, where this coefficient becomes non-zero, etc. So you see the sparsity being shown in this example, where, for example, if I decide to choose the shrinkage amount here, I get 1, 2, 3 non-zero coefficients and 5 zero coefficients. Right? And you typically choose the shrinkage factor by something like cross-validation to trade off the bias and variance of the model. So that's by way of review of the Lasso in simple regression. Okay? Well, the other thing to note is that these are piecewise linear solution paths, which actually was exploited in the Lars algorithm. So Brad Efron and colleagues did the Lars algorithm in 2004, which is a way of constructing this entire path of solutions starting here and taking steps, piecewise linear steps in the profiles as we move along. You can figure out exactly how long these steps are, and you can start here, and in essentially the same order of computation as least squares, you can get the entire path of solutions. Oh, by the way, I wanted to say, seeing the last few days, there's been a number of times I want to ask a question during the talk, so I'm going to try to change things. If you guys want to ask a question during the talk, please feel free, especially if something is confusing. If you're confused, probably someone else is confused. Except for Jamie. Jamie, you can wait till the end of the talk, especially if you want to ask one of these, what's wrong with the whole method thing. So, okay. So. Did you actually have a question? Okay. Okay, so that's the basic idea of the Lasso. I want to talk about an algorithm in a couple of slides, which allows you to solve this problem for large p, well, large n and large p. First, just a couple of examples, which I'm going to go over in detail later in the talk. The graphical lasso for cell signaling proteins. This is a little example. I'm going to show how to apply the lasso, a variation of the lasso, to a graphical model problem. And this is a little example in proteomics where we've got 9 proteins at each node. At each of these, each node is a protein, and we observe data on these proteins, and we're trying to model the correlation, the codependence between the proteins. As we vary the tuning parameter in the graphical lasso, which I'll describe in the talk, it goes from dense to very sparse. Okay? So I will describe how we get this picture and how to interpret it. And then the last example I'll talk about is something fairly new called the fused lasso, in which we put in a second constraint. So not only do we ask for the coefficients to be sparse, but we ask for their changes to be sparse. And that makes sense in a situation where the features have an order. So this is by way of example CGH data in genomics, where you have what are called copy number measurements along the genome. Okay, so each of these points is the log ratio of copy number. Copy number is the number of copies of a gene you have in your genome versus the normal. In cancer, what can happen is you can either have more than one copy of a gene. You should have one copy per chromosome. You could have 2 copies or more, or you could have 0 copies, because either the gene has been copied and amplified, or it's been removed from the genome. So it's of interest to find places where the number of copies is not the normal number, 1. So this assay called CGH, comparative genomic hybridization, is a measure of the number of the log ratio between the number of copies in this tumor sample versus the number that in a normal sample. The log ratio is 0, log base 2, then it's normal. Here, for example, we see along this place in the genome we've got more copies than we should, and here there's maybe less copies than we should. So it's of interest to smooth this sequence along the genome and figure out where the hotspots are. So this fused lasso, which I'll describe later in the talk, gives you this red curve, which is telling us, looks like there's a gain here, and maybe a small loss here. Okay. So I will describe that as well, and some computational problems which are associated with that. Let me start with how one solves a lasso in the first place. Well, in the original paper, what I did is I called sort of a standard convex optimization algorithm, right? And there's been a lot of work in convex optimization. And so it's a convex problem, and you can call a package, and there's a lot of work in numerical analysis for solving convex problems, quadratic programming in particular. So that works. And as I mentioned, the LAR algorithm in 2004, I think, was a nice contribution to this. It's also a quadratic programming algorithm, but it exploits the fact that the profiles, as I mentioned, are piecewise linear, and you can actually exploit that fact in producing the entire path of solutions. So you can get the entire path of solutions, again, essentially with the same order of computation as getting the least square solutions at the end here. And that's the LAR algorithm, least angle regression. And it's very, very interesting work. It also gives you a way of thinking about the lasso as a sort of how it relates to forward stepwise regression. Because the algorithm kind of goes like, you start with no variables in the model, you put the variable in that's most correlated, but you only put it in as much as you can until some other variable has as much correlation. So it's sort of like a smooth version of forward stage-wise regression. So not only is an algorithm, it gives you a way to think about the lasso fit in the context of regression. Okay, but whoops, I got going way off here. Okay. So what I want to talk about today is something new. Coordinate descent is called. And this is a very fast, simple algorithm for the lasso and associated problems. So what's it about? Well, suppose we just had a single predictor. Okay? So a single x, how do we solve the lasso problem? Here's the problem we get. The solution is soft thresholding. This is well known, right? That if you solve this problem for beta, what you get is it says, whoops, I missed a hat here. It says, take beta hat, translate it towards 0 in absolute value by an amount lambda, and return the sign. Oh, sorry, take the positive part and return the sign. So that's just soft thresholding, right? So if beta hat is bigger than lambda, translate it towards 0 by that amount. If it's less than lambda, it just gets thresholded to 0. Okay? Okay, fine. Well, why do we care now? Well, the point of this algorithm is to say, well, we can use this basically for each coordinate at a time. So the basic idea is you have p variables. We're going to start somewhere. Let's say they're all 0. We're going to use soft threshold. We're going to fix p minus 1 of them and solve for the pth one by this formula. Okay? And do that, cycle through the coordinates in turn. So that's the algorithm. So in detail, what you do is you take the residuals of all the other, remove the fit from all the other variables, take the residuals, and then apply soft thresholding to the residuals to get the coefficient for beta j, and then cycle through. That's it. Very simple. And if you do that, it converges to the lasso estimates for the set of variables x1 through xp. Now that actually turns out to be coordinate descent. What is coordinate descent? Coordinate descent is a descent method where you have a convex function, you're trying to get to the bottom. Rather than go along the gradient, say, you go along the coordinate directions. Okay? It's sort of like if you're trying to get to the bottom of a hill, right? You're skiing in a convex ski hill, which probably wouldn't be much fun to ski on, but okay, you're on a ski hill, right? And I say, don't go straight to the bottom, you have to go either north, south, or east, west, right? That's coordinate descent. Why would you do that? Well, it sounds kind of silly, right? Why not go straight to the bottom? Well, if I told you could ski much faster, I mean, suppose you had a peculiar ability to ski much faster north, south, and east, west than any other direction, right? You might do this. Well, that's what's happening here. Turns out coordinate descent is useful here because the coordinate steps are very quick, right? I showed you a simple formula for the coordinate steps. There's no line search, nothing to do. There's a formula for the steps. As well, in this particular problem, the lasso, most of the coordinates are not going to be moved, right? If the solution's pretty sparse, as you cycle through the variables doing the coordinate descent, most of the time you don't go anywhere on a coordinate because it's 0 and it stays 0. So those two features make coordinate descent extremely attractive for this problem. And extremely fast, as I'll show you some timings. And you can also prove that it works. There's a paper which we reference in the computer science literature that shows for classes of functions like this, coordinate descent is guaranteed to get you to the minimum. It's not true for all convex functions. You need additional constraints on the variables, and I'll talk about that a little bit later. But for this class of functions, coordinate descent works, and it's really attractive.
I do have a
Okay. Yes.
You go back to the formula last. So lambda there, shouldn't it be the part of lambda that hasn't been explained by the previous?
The part of lambda, here's the part of the response.
Residual.
Yes.
That you're supposed to have the penalty times the sum of all the L1 norms. So you've got you already know everybody but one of them.
Mm-hmm.
So you only have a little bit of the penalty left?
No, because the penalty is additive, so when you take the derivative, all the other guys, it only
Okay.
yeah, that's correct. Okay, so this is sort of interesting, and this slide's a little unusual, but I wanted to throw this in here anyway because especially for the grad students here, but also for the faculty, because it sort of shows how science kind of proceeds in very odd steps. So I did the Lasso in 96, 97 in Toronto, and I had a graduate student who, as part of his thesis, developed something called the shooting algorithm. And honestly, it was like one chapter in his thesis, and I didn't really understand the chapter that well. I signed it nonetheless, and he graduated. And he didn't really express it in a way, he just really didn't call it coordinate descent, and he didn't do anything with it afterwards. But now I look back at it, in his thesis he had this idea, right? It's equivalent. But nonetheless, I didn't recognize it, and it just it stayed there in a thesis, and he published it as well, but nothing really happened. And then Dobushi gave a talk, Ingrid Dobushi at Stanford about 5-6 years ago, in which she's more of a mathematician than a statistician, in which she had this idea as part of a theoretical discussion of wavelets and algorithms, right? And Trevor admits this. He and I were interested. We went to the talk, came back. That's pretty neat. He programmed it up in R, and it didn't work. And now it's interesting why it didn't work. It's in R that what it didn't work is because in R the temptation is to do things for an entire set of values at once rather than coordinate at a time, because you can store a vector very easily and do vector operations. So what he did was actually he did this, except he didn't update the coordinates until just the end of the cycle, right? That's wrong. You have to update it every time. It's to do coordinate descent. You have to update variable j as soon as you estimate the new beta j. You got to update it. If you wait to the end of the cycle, it doesn't work. So whoops. So at the time, we basically concluded this doesn't work. That's another mathematician going off with some interesting theorem, but it doesn't work. Okay. Well, we were wrong. It does work. We learned in 2006, Jerry was an external examiner at a PhD oral in Leiden of a student who did this for the elastic net. Basically had this coordinate descent idea. And Jerry came back and said, hey guys, have you seen this idea? And we scratched our heads and sort of retraced our steps, and we all realized this is really useful. So we programmed it up properly, it worked. We realized this actually is very, very useful, right? So the credit for this has a long history. A lot of people knew about it, but none of us really realized the power of the method. Right? And then coincidentally, Ken Langen's student at Stanford, Ken was visiting Stanford, around the same time he and his grad student came up with the same idea as well, and they have a paper published around the same time as our paper with the same idea. But it took like at least 10 years to figure it out. And why am I excited about it? Well, I should say, first of all, there's another second part of the idea is that, so we know how to do it for a fixed lambda, the cyclical coordinate descent, but in addition, we do it along a path. We start with very large lambda, that's very sparse model, everything's zero, and then you basically, you move in you increase lambda using each previous solution as a warm start. So you get the entire path, along a grid, and as you move along, things don't change much, right? Each solution is a very good start for the next thing. So you go from very sparse to very dense along a path of lambdas. And the amazing thing is that at least the basic algorithm is so simple. It's really 73 lines of Fortran. And whenever I give this talk or a version of this talk, especially to people, computer science people who are there, they see Fortran and they kind of laugh. Fortran, you guys are still using Fortran, right? Well, Friedman, if you know Jerry Friedman, he's a master programmer. Like the other part of this is that Jerry Friedman has found some really smart ways of making this fast. Some tricks, which he come into our office every day and say, I realize I can do this, this, and this to save a few milliseconds, right? And we kind of laughed at him. But then at the end of it, we're doing something millions of times, every little thing helps. And the result is an amazingly fast algorithm in Fortran. But the idea is, you can program up the basic idea in any language in a few lines. And now we have a package which is available right now called GlimNet, which does this for regression, the logit model, multinomial model, and it's available now in CRAN, in R. And there's also a Fortran program there, which it calls if you happen to want to use Fortran directly. And we've extended it to lots of different models, the last two of which I'll talk about today. So again, GLIMNet. The logic model, for example, for a binary response, you're all familiar with it. In our paper, we have an example where, so that's the model. Now it's log likelihood, binomial log likelihood plus absolute value penalty. A simulated example, a large simulated example where the data as well are sparse. So if your data is sparse, which sometimes happens with web data, you can exploit that as well in the arithmetic, right? So this was one example from our paper which we simulated. And we compared it. Steve Boyd's a good friend at Stanford. He's a big name in convex optimization. He wrote the book on convex optimization, I mean the new modern book. And he has very good algorithms, interior point algorithms. And we have sort of a friendly competition going on with Steve about these kinds of problems. And on this problem, his algorithm takes 3.5 hours. His algorithm is interior point algorithm. It's a general algorithm for convex problems. 3.5 hours, this takes 1 minute. Okay, so it's really quite remarkable. And this is a serious algorithm, and it's not just an off-the-shelf algorithm. They actually adapted the algorithm to this problem. Still, there's a large gap between the speed of these things. And the reason is, I mean, this is a general algorithm to some extent. This problem is extremely specialized, right? It's a convex optimization problem. It's extremely specialized, a very simple penalty. And if you fully exploit that, you can get an enormous gain in speed. Okay, and this is just an example of using the multinomial version, which you can do this with GLIMNet. This is some common microarray data, 14 classes, cancer classes, 16,000 genes, 144 training samples. And I put here sort of a battery of commonly used methods for high-dimensional classification. Support vector classifier, near shrunken centroids, k-nearest neighbors. This is the guy here, which GLIMNet can do now. And I've recorded both the cross-validation errors, this is 5-fold cross-validation, or test errors on a separate test set. And basically, the method is competitive with the best methods here. Also, because of the Lasso penalty, it gives you a nice sparse solution. So support vector machine, if you don't do any kind of feature selection afterwards, uses the full gene set, whereas this has the advantage that with the L1 penalty, it gives you a much sparser set of genes. So. And again, now you can do this on this data set really in a few seconds because the algorithm is very fast. So this is the kind of thing you get with the new GLIMNet package if you want to try it. Again, I'll pause for questions if there are any because I'm going to switch gears into the graphs now. Yes, Doug?
Rob, can you go back to that other example? I'm trying to figure out what that matrix looked like, the N by P matrix.
Here?
Yeah. How did you? Oh, it's a sparse matrix.
Sparse matrix, yeah. Okay. It's like 99% zeros.
Okay. And does Boyd's algorithm use sparse matrix methods on it? Okay.
Yep. But it's very sparse. That's why you can do, I mean, I'm not claiming I can solve any kind of a non-sparse problem of this size in 1 minute. It's very sparse.
Yeah.
So that's why you can get something in a minute.
Yeah.
You set lambda to 0, you're basically solving a system. But what would your method do? I was just wondering, I mean,
when lambda equals 0, what you get is the, well, in least squares, I guess, you get the minimum L1 norm solution. So you get a path of solutions that, if you move lambda from big to 0, it gives you the minimum L1 norm solution among all solutions with 0 training error. Right? Because that's it's got an L1 penalty. So it's picking out, among the least square solutions, it's picking out the one with smallest L1 norm. And the same thing here. It's picking out the one that gives you the largest value of the log likelihood with minimum L1 norm.
Oh, no, I thought if it's not there, if the L1 penalty is not there, right, then you just solve.
Well, yeah, but you're moving in a path towards that. So you can only really talk about the limit as lambda goes to 0. You're right, at 0, there's not a unique solution. Okay. So switching gears a bit, graphical models. So how can you apply the Lasso to graphical models? Here's a little example. P variables measured on n observations. This is a little example in proteomics where I've got P proteins measured on n cells. And I want to fit a graphical model undirected to the data. So just to remind you what these graphical models mean, you draw a graph, and if you leave out a link between two nodes, it means the variables are independent given the other nodes. So here's a little example with 5 nodes. And imagine I have 5 proteins. I observe the proteins on a few 100,000 cells. I draw this graph, and what this graph means is I don't have an edge here between x4 and x5. It means these two are independent given the other guys. Right? Whereas if there is a link, they're not independent given the other guys. That's sort of how these graphical models are typically encoded. And you assume that the observations are normally distributed, so you're really talking about the covariance between the random variables at the nodes. Okay? That determines whether things are independent given the others or not. So a graphical model, a basic problem of graphical models is to figure out, given some data, what is the best graph to describe the data, to describe the joint distribution. Should I put an edge between these two nodes or should I not? And that depends on the joint distribution, the covariance or correlation between these two guys given the other variables. Right? So we want to simultaneously find a graph that describes the joint distribution well. And that's a problem in graphical models. So Nicholas Meinhausen and Peter Buhlmann, Nicholas here, had a very nice paper in 2006 which had the following idea. Well, if we want to know, we want to somehow figure out whether we should include edges or not, that sounds like a sparsity problem. So their suggestion was, well, use the lasso for each node at a time. Just in words, I'll come back to this slide. But basically, the idea is that here we have our data. Let's first pretend like this is the response variable and the other guys are the predictors. Do a lasso fit of this guy on the other ones, and then look at the coefficients. And if the coefficient between x1 and x5 is 0, then we leave out the edge. Otherwise, we include the edge. You do that for each node in turn. Each node gets to play the response variable role, and all the other variables are the predictors. Well, there's a problem, because now you're going to get sort of 2 shots at every edge, right? When I do x1 on the others, I'm going to get a coefficient for this edge. But similarly, when I do x5 on the others, I'm going to get a coefficient for this edge. Well, they suggest, for example, include an edge if there's a non-zero coefficient for E in the lasso fit for x1 on x5 or for x5 on x1. So sort of a min rule, okay? Or you can do a max rule, either one. But some way of combining basically the regressions of each variable on the other nodes. And from that, you can determine whether to include an edge between every pair of nodes. Nice idea, and they prove under certain conditions that if you have a graph with sparse edges, it then goes to infinity, that procedure produces the correct graph with probability 1. It's consistent, okay, under some conditions. And that's the 2006 paper. So I basically have said all this. It's basically a node at a time lasso. Each node gets to play the role of the response variable. Use the coefficients from the lasso equations, from the regression equations from the lasso, to tell you whether to include an edge or not between every pair of nodes. Okay, that's their idea. Well, that's not quite exactly solving the problem, right? It's treating the graphical model as a series of regression problems. Well, you can modify this thing with the lasso to actually to solve the problem exactly. So what problem exactly? I haven't posed the problem yet. Here's the way of stating the problem. Our data is normally distributed. I'll assume the mean is 0, covariance sigma. Sigma is what's of interest, the 0, not the mean. Recall from multivariate normal theory that 2 variables are independent given the others if the jkth entry of the inverse matrix, these are the partial correlations. If this is 0, then variables j and k are conditionally independent given the others, right? So the inverse of sigma is what tells us whether to include an edge between variables nodes I and j or not, right? So in other words, we want to know what sigma is, and we want a sparse estimate of sigma. Particularly, we want to know whether symmetries of sigma are 0. Sorry, sigma inverse. We want to estimate sigma inverse, and if there's a 0 entry from the estimate, we're going to leave out an edge between the corresponding nodes. So as a mathematical problem, here's one way you can state it. And now, if I say, well, my data is normally distributed, and I have an L1 penalty on sigma inverse, here's the problem I'm solving. Turns out the log likelihood of the data can be written in this way. So theta is sigma inverse. That's the guy of interest. Log determinant of theta, the normal PDF can be distilled down to the trace of S times theta, subject to the L1 norm on sigma inverse. The data is an S. This is the empirical covariance matrix. So here's the data, and here's the parameter I want to estimate. So this convex problem is what I get if I start with data being normally distributed and ask that sigma inverse be sparse. Okay? And Jan and Lin, I think, were the first that I saw that proposed this idea as a way of estimating sigma inverse. This is a convex problem. But it's kind of hard, right? This is a complicated object, log determinant of theta. Well, it turns out that you can rephrase a problem in a very useful way. Here's sort of a conceptual way of thinking about it. So the method I just talked about that Meinholz and Buhlmann proposed can be thought of this way. What we're doing is, here's my notation, we're doing a lasso fit of each variable on the other variables, right? xj on x minus j, that's what I mean by that. So the node at a time algorithm I already described has this form, right? Well, I can think of the lasso as taking not as input the raw data, but covariances, right? Because when I do a regression, I don't need to know x and y. I just need the covariance between x and x and y. So I can write it rather this way. The naive node at a time algorithm uses the covariance between the features, all the other features, and the covariance between the node of interest and the other features, right? That's just an equivalent statement to this with some Lagrange multiplier, some lasso-bound T. Well, to solve this problem exactly, you just need to, all we do is replace x transpose x by the sigma. So this is the idea here. Think of the graphical problem we're solving here. The node at a time algorithm says do a regression of each guy on the other guys. But the problem is not actually p separate regression problems, right? They're actually coupled together on a graph, right? So when I learn something about sigma from one node regression, I should use that in the other regressions. They're sharing sigma. When I do the node at a time algorithm, I'm not acknowledging the fact that sigma is common, right? This explicitly acknowledges the fact that if I learn something about the covariance between two variables from one regression, I got to use that in the other regression. So it's a natural thing that follows from the problem. So it turns out that this simple algorithm, a modified lasso, it's just a lasso fit using the covariance of the x's from the model rather than the empirical covariances, solves this problem exactly. Okay? And this is the graphical lasso, as we call it. It's a modified lasso which simply replaces, well, again, the empirical covariance by what the model tells you currently about the covariance. Okay? Why this should work is not clear. I mean, conceptually, I hope you think it's reasonable now, but the fact that it works is actually kind of subtle. These guys in computer science wrote a very nice paper which pointed this connection out, but they didn't really use it fully. They went on to then do a different algorithm, but they're the ones that really pointed out that if you look, well, I'm not going to give you any full details, you have to look at the paper, but essentially if you look at the subgradient of this equation, this complicated guy, it has the same subgradient as a certain least squares problem arriving from the lasso. So this complicated guy shares a subgradient with a very simple guy. And this says basically you can turn this, that says you can turn the complicated problem into a simpler problem, really, because they share the same subgradient. Yes?
In your normal one, do you exclude diagonal elements?
Yeah, so either way, like the software allows you to either exclude it or not, and it doesn't really.
Why would you want to exclude?
For a graphical model, I agree, but sometimes you might want to use this, you're not even using it for a graphical model, you want an estimate of sigma, or sigma inverse, in which case there are situations where you do want to shrink sigma and sigma inverse. But it doesn't really change the algorithm, it just means, the algorithm has the same form, it's just that there's one step that's different. But on the software, you can pick whether you penalize the diagonal or not. So what's the idea there of the algorithm? Well, again, we're going to use coordinate descent. So I've said now, to solve the graphical model problem, the graphical estimation, you need to do a lasso fit cyclical through the variables, right? For each of those lasso fits, we use the coordinate descent algorithm I just showed you. So it's sort of two, we cycle through for each of the algorithms, let me go to here. So we do a lasso fit of each of x1 on the other ones, modified lasso, right? The covariance has changed, otherwise it's the same. For that thing, we use the coordinate descent algorithm I just showed you at the beginning. And we move on to x2, do the same thing. And we just cycle through the nodes, and again, it's very fast because things don't change very much, typically, right? So it's all just coordinate descent. It's actually sort of a block-wise coordinate descent, because each node represents a row and column of the covariance matrix. Okay. So there's a G-Lasso function available in R which does this, which you're welcome to try. So by casting the problem as a lasso, a modified lasso problem, we can then use algorithms we have for the lasso, like Lars, or in particular like the coordinate descent algorithm, which we found is so fast in the least squares problem. Speed comparisons, again, very fast. Compared to the state-of-the-art optimizer, and it's very fast. Right. So again, the advantage of the coordinate descent algorithm for the least squares problem is inherited here in the graphical problem. Okay. This is for normal networks. Things are binary. I have a grad student who's working on this, and you can extend this in principle. It doesn't work so well because the partition function still remains at the hurdle. So this speeds up part of the problem, but not the major part of the problem. So that's still a work in progress. We're not nearly as successful in this situation, which is inherently harder. We're working on it. So this is the example that I showed you at the beginning. These are from flow cytometry data, 9 proteins on a few tens of thousands of cells. And this shows the graphical lasso path as we go from very dense to very sparse. And the nice thing, I think, by casting as a regression problem, you get to use all the things you know about regression, right? You can cross-validate over lambda to figure out where you should be in the path. You can see how well it predicts the joint distribution. So it makes it sort of more familiar doing it that way. It also brings another thing. After we did this, we realized, well, what if we sort of didn't have a penalty at all? Like, what if we said the following problem? I have a little graphical model with some data, and I want to fit the model, leaving out some edges. No penalty, just fit these edges and leave the ones out that aren't there. Okay, so that's a simpler problem in a sense. No L1 penalty. How would you solve that problem? Well, intuitively, you just do the same thing, except when you do a regression of each node on the other guys, you leave out the variables. So when I'm sitting at x1, I can do a regression, a modified regression again. Remember, it's this covariance has to be modified. But I leave out x3, for example, on the regression of x1 because there's no edge there, right? So it's just go around and leave out the edges that the graph tells you to leave out, right? You can prove that actually gives you the MLE of sigma with the constraints imposed by this graph. Right? Very simple. And surprisingly, I've checked with the experts that this is not an area we know much about. We checked with the experts, and this seems to be unknown. A lot of there are algorithms for this for graphical models, lots of them. Some are simple, some are complex. This simple algorithm seems to be unknown. Again, this connection between the log likelihood and the least squares is a little bit subtle, and I guess people hadn't realized that that connection existed, and you can exploit it to essentially turn a graphical model problem into a least squares problem. So this simple algorithm you can show works for fitting a model with some links removed from the graph without any further penalty. Or you can have some of both. You can say I want to leave out some edges and I want to penalize the rest. It's all just one big penalty problem, right? You can use the same paradigm for problems like that. Let me pause for questions before I go to the third example. Okay. So, that's one last thing is one of my students that did Daniela Witten is using this idea of joint covariance estimation for regression. It's something we call the SCOUT. So the basic idea there is to say I'm doing regression of y and x. I'm first going to, rather than go to y and x, I'm going to use the graphical lasso to get an idea of the joint distribution between x and y. Shrink the joint distribution, shrink the corresponding sigma, and then use that to obtain, hopefully, an improved regression coefficient of y given x. It has the same flavor as the elastic net. The elastic net shrinks towards the identity. This shrinks in a more general way. So this is, I think, it's promising. And there's a paper on our website which describes that, called the SCOUT. Okay, so now the third topic is the fused lasso. And there was actually mentioned by Eric yesterday talked about an application of this kind of idea in dynamic networks. So the idea of the fused lasso is as follows. Well, this is the Lasso regression, although I have no predictors here, right? So this is actually a simpler problem. I have a sequence y. I want to approximate by a sequence beta. I have the Lasso penalty, but I'm going to add another penalty, which is a penalty on how much the coefficients change. Okay? So we call this a fusion penalty, because as you see, what happens in the estimation is that the penalty causes the procedure to fuse together consecutive values of beta. And what do we want to use this for? Let me come back to this slide. Data like the CGH data I mentioned before. We have data that has, the features have an order of some sort, in space or in time. And we want to approximate the data by a sequence that's both sparse and smooth. So again, this is the CGH data where this is the 0 line, this is my data points. I want to approximate it by this red guy, which is reasonably smooth, right? I mean, he's sparse, he's 0 in here. But then he's non-zero where there's hotspots of either gain or loss, right? So it's basically a signal approximation problem where I want the signal to be sparse, mostly 0, and I want it to be flat in cases where it's non-zero. Well, this penalty kind of, it gives us, it encourages that to happen. This encourages the sparsity, and this encourages the smoothness when it's not sparse, when it's not 0. And I have two tuning parameters now. This guy controls how non-zero it is, whereas this guy controls how smooth the plateaus are, how flat they are. Okay? We call this the fused lasso. And this is interesting. Well, first thing that's interesting is that one thing that really surprised us, you can imagine doing the coordinate descent for this problem, right? Why not? I mean, just hold each variable fixed and optimize over the other guys, right? It's convex. It's strictly convex. Well, lo and behold, it doesn't work. Coordinate descent doesn't work. It's quite remarkable. We thought for the longest time our programs had bugs in them. Well, actually, what happens is it's because, well, these are not smooth penalties. You can have a cusp, and the algorithm can get stuck in a cusp. So the skier wants to travel to the bottom. He needs to ski at a 45-degree line, but you're insisting he ski along east, west, and north, south. When you have this penalty involving pairs of parameters, it turns out you can get stuck. So simple coordinate descent does not work. Okay? But you can fix it to work. You can modify it by moving pairs of parameters. And we have an algorithm which does that. So this was interesting computationally. It's harder than the simple lasso, but it's solvable. But it's a surprising thing that happened that coordinate descent didn't. Right? And this is one of the reasons, by the way, that computer scientists, like if you look in Boyd's book, a lot of books, they don't even mention coordinate descent. It's like it's not even on their radar, right? Because it doesn't work in general. It only works in really specialized problems. And here's something which is already still pretty simple. It doesn't work. That's the reason why coordinate descent kind of has a bad name in optimization, because it just doesn't work very often. But when it does work, as you've seen, it really, really does work well. So, yes?
It does work whenever the thing is differentiable, right? I mean, so that's very important.
When it's differentiable, yes. But when it's convex is not enough.
Yeah.
Strictly convex isn't enough. I find it surprising, but yeah, you're right. It does work if it's differentiable. So this sort of gives you an idea of what happens as you vary the lambda parameters. In the top left, they're both about 0, and we just interpolate the data. As we move along to the right column, lambda 2 is getting bigger, so we're forcing more and more of the plateaus to be flatter. As we move down the rows, lambda 1 is getting bigger, we're forcing more sparsity. And in this case, it's hard for you to see probably. A good solution maybe is here. Or maybe, actually, this is a good solution, right? It's pretty much 0, and it's non-zero in the right places. So you have two tuning parameters to deal with. It's inconvenient, but it's doable. I won't say anything about this except to say that we've done, Pei Wang and I and other grad students have done comparisons. There's a lot of people who have worked in CGH data and compared a lot of different proposals for estimating the hotspots, and this method seems to be extremely competitive with all the best methods. So it's simple, it's convex, and it does seem to work quite well. Okay, so two more applications of the fused lasso. This is a current one with, again, Novak, one of my grad students. Multi-samples. So this is another problem people work on. So now this is, for example, in breast cancer. Each of these is a CGH plot for a patient, right? Patient 1, patient 2. The red are the gains, the greens are the losses, right? So in this study, there's something like 60 patients, and I've showed you 9 different CGH plots for 9 different patients. The problem is to find common patterns among the patients. Right? What often happens in cancer is you've got sort of subclasses of cancer. Right? You might have a certain change in half the patients and some other changes in the other half of the patients. So it's important to figure out the common patterns among the patients. So one way to do that is to apply something like the fused lasso to each individual sample, right? And then just sort of try to compare them. But there's an inherent problem with that. Like I might have 2 patients that show the same change at the same place. If I sort of do a marginal projection of the data down, I'll see something like this. But this could also have occurred from a situation where patient 1 has this change and patient 2 has a different change, and I sort of see the same thing when I look at marginally. So the point being, you can't sort of just summarize, collapse down over all the patients. You need to sort of look inside each profile and figure out common patterns. So what my student is doing is kind of a principal components with fusion. The idea being we have our data for the individual patients, and we postulate there are ingredients, like principal components, which are common to all of them. And there are weights, so each patient profile is composed of a combination of these profiles, right? And these profiles have a fused lasso form. And so it's like principal components, where these are the components and these are the loadings, and these are both unknown, and you have to uncover them. And we have an algorithm which is sort of like principal components, which uses fused lasso to tell you, to try to figure out the underlying components and the weights with which they combine to give the individual patient samples. Okay, so that's ongoing work. And in this data, for example, we found these components. This is, again, all very preliminary. So we found, like, the major change you could find was sort of a big gain in this arm and a big loss in this arm. So we hope this will be a good way of looking at a series of patient samples and figuring out the common patterns of change among those samples. And finally, let me just talk about the 2D fused lasso, which might be useful for two-dimensional data. So this is all very, it's an obvious extension of the first one, right? Of the signal. So now we have a 2D image, y, so y, I prime. We're going to approximate it by a surface, beta, which is smooth in smooth in up and down. So sparsity on the betas, but also sparsity in the vertical direction and sparsity in the horizontal direction. Okay, so it's now rather than a signal, we have a 2-dimensional surface we're approximating in this way. So now, and we're insisting on beta being sparse, being smooth vertically, and being smooth horizontally. Okay. It's a 2-dimensional fused lasso. Friedman was, Jerry's actually retired from teaching, but he's still around the department. In the last year, he's been really, really working hard in this. Doing some very impressive programming, and he nearly gave up, but he got this to work. It's got to be quite intricate. I mean, it's a convex problem. It should be simple, but it turns out as you start to do this coordinate set, you have to worry about the local, the cusp problem I mentioned, and you have to fuse together points, and it requires some impressive programming, but he did finally get it to work. So here's an example. Let me just show you a little toy example of this working. Right. So this is an example. Again, I don't know a lot about image processing, and I hope that those that do know might think about ways this might be useful. This is just a little toy example. This is a grayscale image we just made up. Here's the data. The first, make it a little bigger, maybe. It takes a while to draw, but I'm going to redraw. So the top left is an image which is there's a black background, and then there's square patches of various intensity. So here's the original image. No, there's no noise in this image. We applied the fused lasso. It's all automatic, so it has to pick the 2 tuning parameters, does so by cross-validation. It picks the tuning parameters, and then it just gives you the estimate. And it gave you this estimate. And you can't see very well from there, but it's nearly perfect. But there's no noise here yet. Okay. So now here we added quite a bit of noise. It probably looks fuzzy to you, but it actually is quite fuzzy. So the image is there, and I just sort of overlaid it, normal noise. So it looks very cloudy. It's very, okay. And it's quite impressive, I think. Given this data, it produced this reconstruction, right? Now again, it's using the fact that I'm telling it that the regions you're looking for are contiguous, right? I'm using this fusion penalty, but it's telling you whatever you're looking for, they're going to be contiguous patches. And it's producing that reconstruction, which is a little worse than this, but it's still pretty good. So again, this is a way of imposing smoothness in two-dimensional images or even higher dimensional images. Sparsity and smoothness in the image. And again, it's all convex, so in principle you can solve it with a convex optimizer. So again, original data, reconstruction, noisy data, reconstruction. Okay, so you can see my time's almost up, which is good because I'm about done. Back to here. So discussion. Okay, so I think that the Lasso penalty is useful for fitting a wide variety of models in large data sets. And what's got me excited real recently is the algorithm which allow us to apply the method to large data sets. So I think that's going to enable application of these methods to a lot of other settings. And I mentioned some software already available, the Lars algorithm, which does the path, the piecewise path, which is from the Efron et al. Paper. That's in R. CGH fuse Lasso. This is a function that I wrote with my graduate student Pei Wang, which does these fuse Lasso for CGH data, the profiles you saw. Graphical Lasso for the networks, and GlimNet, which is this nice and really new package which does coordinate descent for regression and the logit model, multinomial models, etc. And this has just been out for about a month now. So I invite you to try those, and I'm sure you'll find bugs, and please be patient, but let us know about them. And finally, you can use the Lasso to prove Efron's last thing. That's your cue now to.
Wild applause. Any questions or comments?
I wonder if a similar effect to the fuse Lasso could be achieved by, say, thresholding the signal in the time domain itself and in say, the wavelet domain, or in some kind of differencing domain simultaneously?
I think you're right, probably, because if you threshold in the time domain to get the sparseness, and then in the wavelet domain to get the smoothness, you might get something equivalent. But they're not orthogonal. Well, whether you get exactly the same thing, I'm not sure, because the two penalties are not kind of orthogonal either. So whether you could solve the same problem, whether you could recast this problem in the way you said, I'm not sure, but it sounds interesting.
That relates to that. Can you do that when you have arbitrary linear combination? So your L1 penalty sits on, I mean, you've showed us where you have the identity linear combinations, then you have showed us where you have this nearest neighbor linear combinations. I think you were talking about wavelet linear combination. I mean, could you run the same? That would be amazing, because there's so many problems out there that, well, basically the L1 penalty is sitting on a different linear space than your variables live in.
I see.
Quite generally different linear space. I mean, wouldn't make sense that you have to write new code for each of these cases, but something like I give you a matrix and you can run the code. That would be amazing.
Well, okay. The current code does not do that. Now, although I think with a general convex optimizer, you could call it in such a way as to do that. To do it efficiently through the coordinate descent would be interesting, but we don't yet have code to do that. But that's an interesting point. To ask for constraints on different
basis pursuit paper, you just throw any matrix in, and you can get lots of things by choosing special matrices. So that may be what he has in mind.
Yes.
Especially like your graphical Lasso, so is it heavily relying on the fact that all the distributions of the components are normal? Because very often in graphical models you have to cope with discrete distributions, or even mixed continuous discrete distributions. Would your method then also work well?
Well, I mentioned that the answer yes, it does rely on normality, and if they're all discrete, then the problem gets substantially harder. I mentioned that because of the partition function. So I have a student working on that, but the graphical Lasso idea really doesn't work as nearly as well, because the major part of the problem is somewhere else. And then if you have, as you say, if you have a graph which is mixed, some continuous, some discrete, I think still it's hard. I think as soon as you move away from the normal distribution, where very nice things happen, the problem gets much harder. I mean, it's not necessarily intractable, but it's not going to be nearly as simple to do. The current software assumes normality,
You have a solution path for graphical lasso?
Solution path. So what the question is referring to, like the Lars it gives you a solution path for least squares. I mentioned that it gives you the entire solution path. For the graphical lasso, we haven't worked that out. It's not really, you see, since you're solving p problems at the same time, the solution paths, I think, are not linear anymore. So we haven't worked it out, but we also didn't think it would be that, like a good computational approach, but it'd be interesting to do.
If I've got a problem that is not sparse or not very sparse, when should I use lasso and when should I use ridge regression?
Well, so there's no real answer to that question except to try them both. I mean, I don't mean to evade the question, but that's really the truth. The thing is, you don't, I guess first of all, I don't think one knows when a problem is sparse or not, right? You don't know what the truth is, and you don't know how much, whatever the truth is, your ability to uncover it depends on the amount of noise. So, I mean, it's sort of the generic answer is if things are reasonably sparse, use the lasso. If things are usually are quite dense, I would use ridge regression. So that's my sort of general answer, but honestly, I would always try them both, using things like cross-validation or test error to tell you how well you're doing. Because you just don't know in practice, and it's easy to try them, right? That's one nice thing about being a statistician. Our lab is just a computer, and we do things very quickly. So always try more than one thing. But if, sort of in general, sparsity will favor the lasso, and things less sparse will favor ridge.
In the other applications like the fused lasso and the graphical lasso, do you require things to be normalized like in the original lasso?
In the fused, let's see.
How would you normalize?
Well, in the fused lasso, there's no regressors. There's no, so there's no question.
That wouldn't be an issue, yeah.
The graphical lasso, you're starting. You can either start with the covariance matrix or the correlation matrix. So that's where the issue comes up.
Yeah.
So that's. I'm just drawing a blank here. I guess it does matter if you don't penalize. Yeah, it does matter whether. So you just have to choose to start with either the correlation matrix or the covariance matrix, and that's akin to either normalizing or not.
Yeah. That would give you different results.
Yes. Yeah.
In graphical lasso, how you guarantee your model? I mean, since your estimate the inverse of the kind of covariance matrix, your method should guarantee positive definite. How you guarantee that?
It does. Well, it's not our method. I mean, the other people who have written about this, like the Banerjee et al., they prove that the estimate is positive definite as long as the regularization parameter is positive, the estimate's positive definite. So the solution to that convex problem is positive definite. Other people have proven that. Was there another?
One more question. Then we should break.
Can lasso be applied to a nonlinear regression problem?
Nonlinear regression problem. So you don't mean like non-parametric regression. You mean
just a nonlinear.
In principle, yes. I've never really seen it.
But for linear regression, you can get an analysis form for the solution. But in nonlinear problem, you can't get find the analytic form.
And it might not be convex too, say. Yeah.
So it's hard to find
It's worth trying. I've never investigated that.
Okay, let's thank Rob again.